college lab. Now we're going to show you how to use cheesecloth. Now here's what happens when you use dry cheesecloth. Put it down in your funnel. Right here we've got homogenized liver. Beef liver, of course. Now, when you pour it in here, you're going to notice that it doesn't work very well. And that's because it's not wet. You can see instead of filtering the liver, it just kind of absorbed it. So let's start over. Now we're going to moisten this cheesecloth with butter. Alright, now that it's wettened, it can filter our liver. As you can see, it's gotten all the chunks. That's how you use cheesecloth.
Alright, so you're going to take your homogenized liver and this is going to be mixed with a buffer solution. This will probably have already been set up for you before class. It's basically going to be a liver enzyme solution. And what this is used for is basically create a reaction that was going to have oxygen raise up your discs in your hydrogen peroxide dilutions. Now when you're going to do this, you have to be very careful just to grab one disc. As we have here. Then you're going to dip the disc in the liver enzyme solution. And we count to 10 seconds. Swirl it around a little bit. And once you've had it in there about 10 seconds, you can take it out and blot it to get it dry. Not completely dry, but just not, you don't want it soaked. And then once you place it in your hydrogen peroxide solution, at the very bottom, you start counting at 0. You use a stopwatch for this. When it rises to the top, as we see it just did, you're going to take the time. You're going to use your various times for your dilutions to make your graphs. And that's what this is used for.
Okay, here's something you need to have done before class. You need to figure out how many milliliters of a 3% stock solution of hydrogen peroxide you need to add to a phosphate buffer to get these concentrations of hydrogen peroxide. Now your final volume needs to be about 20 milliliters. You can find these numbers using M1V1 equals M2V2 as illustrated in a previous video.
Okay, now before you can actually make the graphs that you'll need to for this lab, you're going to need to get a lot of data from the lab. Now you're going to have to fill out in your lab book a sheet that looks much like what we have written up on the board. Now here we see our hydrogen peroxide molarity concentrations. Next we see replicates. Now these are going to be the different runs that you do for each different concentration. Now for the first one, let's see, say the first time we had a 3-second, a 5-second, and a 4-second run. So then we're going to come over to this next box, which is wants the mean of our runs. So that obviously would be 4 seconds. Our next box wants 1 overtime, which we see would be 1/4. Now this box wants the reciprocal of our molarity concentrations, which in this case would be 6.25. Now once you finish out getting all the data you need for this sheet, the next thing you're going to do is figure out what goes for what graph. Now your Michaelis-Menten plot is going to use your different concentrations along with your inverse of your time, which is velocity. Now the Lineweaver-Burke, on the other hand, it's going to use the inverse of velocity, which just happens to be time. So it's going to use this right here along with the inverse of your molarity. And those are the two graphs you're going to need to use from this data. So after you've collected your data from the lab, you're going to need to plot this data on 2 different graphs. Now the first graph is called a Michaelis-Menten plot. Now what it's going to do basically is plot your hydrogen peroxide concentration and molality, which you had figured out before class, against your velocity, which is also 1/time, obviously. Now you're going to get a graph that should look something similar to this. Where at first we're going to see steep rises, and then eventually it's going to kind of even out. Basically it's going to have a maximum point. Now this point where we think that it maxes out, we're going to call Vmax, velocity maximum. Now if we go to the middle, the halfway point, we have 1/2 Vmax. Now finding 1/2 Vmax is the way we're going to find Kn. Km is the concentration that it would take to reach half of your maximum velocity. So in this instance, it would be right about this point. That is how you find the Km graphically.
Alright, now I'm going to show you how to plot your data using the Lineweaver-Burke plot. Now what you're going to do is plot time on your y-axis and 1 over your hydrogen peroxide concentration on your x-axis. When you do that, you should get a line similar to this. Now what that means is this formula, and you should notice it looks a lot like y equals mx plus v. You're going to use this formula to find your Km and your Vmax. Now your Vmax is simply your V, or your y-intercept, and that's 1 over Vmax. Once you know your Vmax, you can find your Km. Now your slope should be Km over Vmax. Since you already know your Vmax, and you already know your slope, you should easily be able to solve for Km. And that's how you use this plot. Alright, now I'm going to explain to you how to find Km and Vmax using the Lineweaver-Burke equation. After you've collected all your data, you should get a line of fit. It should be something maybe like this. Alright, since this formula follows the y equals mx plus v format, we know that our slope is equal to Km over Vmax. So let's go ahead and write it out. Km over Vmax equals 0.5. Now, we know that 1 over Vmax is equal to 5. So we can write that down. We can easily find Vmax by putting 1 over 5, which is 0.20. Now that we know our Vmax, we can plug it into this formula to find our Km. So Km over 0.2, which is our Vmax, is equal to 0.50, again, getting that from up here, is equal to 0.10. And that's how you find your Km, and that's how you find